Hello, everyone. My name is Adam Gonczarek, and I'm the Chief of Technology at Alphamoon. And my talk is going to be about how we can enhance machine learning algorithms with a human-in-the-loop approach. Okay, so here is the agenda of my talk. I'll start with a brief introduction showing you what is the motivation behind studying human-in-the-loop approaches. And then I'll show you two completely different ways how we can involve a human in the process. And one is in the training phase, and the other one is in the prediction phase. And the latter one is something that we are currently working on, and it is especially of interest to me now. Okay, so I would like to start with showing you two perspectives and two different motivations while working on a machine learning project. And this is also a story of my life, because most of my professional career, I worked in academia at Wrocław University of Science and Technology, where I did my PhD and machine learning and then worked as an assistant professor for a couple of years. And I hope that you will agree that very often when you are doing research in machine learning, the ultimate goal is to come up with a model or an algorithm that outperforms current models on particular tasks, in the sense that it achieves higher accuracy. And whenever during this talk I will say accuracy, you can think of your favorite metric for evaluating a model. So for example, here we have some metrics. You can think of classification accuracy, AUC, F-score, mean average precision, log likelihood, and so on and so forth. And so pushing state-of-the-art on machine learning tasks is just a common way to do impactful research, and it is nothing wrong with that. It is how we do the research. And then over 3 years ago, I came to business, and together with my colleagues, we started Alphamoon. And I quickly realized that when I was meeting potential clients and trying to sell our machine learning services, and I was speaking about model accuracy or how great F-score we can achieve, it wasn't really something that they wanted to hear from me, because business cares about money and what business value machine learning algorithms can bring to the business. In general, there are two main sources of business value from machine learning projects, and you have them in the slide. So the first one is cost reduction, and the other one is sales increase. And during this talk, I would like to especially focus on cost reduction, because usually it is roughly equal to the level of automation provided by machine learning. And by the level of automation, I mean that it is basically how much of human work can be done by algorithms. So if a task can be done end-to-end by an algorithm, then we have 100% of automation. And the first question we should answer is, when machine learning generates value for a business? And the answer is that it depends on a particular task. And to illustrate that, let's look at this axis. So on the most left side, let's put the most naive model we can come up with. So for example, just a random prediction. And on the most right side, let's put the model that is achieving the highest possible accuracy. So sometimes the lowest possible error is also called the base error, and it is not necessarily zero for various tasks. So the highest possible accuracy, it will be just 1 minus base error. And somewhere between, for example, somewhere on the right, we can put human level performance. Somewhere before that, we can put current state of the art, and so on and so forth. And now look at the first example. So let's imagine that we want a system for targeting customers for online shopping. So such a system generates value if only the model accuracy is better than the naive prediction. So, for example, having a system with such accuracy will have some value. Of course, if it is better to develop a system that is somewhere close to the state of the art or even exceeding the current state of the art, because it will be targeting customers better and, of course, generate more income to our company. And now look at the second example. So now the goal is to develop a system for breast cancer detection using mammographic data. So let's imagine that we want to replace a doctor with such a system. And for now, let's put all the legal aspects aside. So such a system can't be autonomous unless it performs at least as good as a doctor. So for example, here we can have a system that is outperforming the human level performance. And the question is, what if we create a system with the accuracy that is much lower than the human level performance? And then each example has, of course, to be double-checked manually by a doctor, because the risk of error is too high to be acceptable. And because of that, the level of automation will be low. Okay, so in this slide, you can see how a typical machine learning project development process looks like. So the curve you can see is also called the diminishing returns curve, and it describes the dependence between the accuracy of your system and the effort you have to put in developing it. In other words, further you go with the project, the improvements are getting smaller and smaller and smaller. And on the right, you can see different sources of costs of a ML project. And these are, for example, data acquisition and labeling, which are very often the major cost of the project. Of course, algorithm development, and by algorithm development, I mean not necessarily just developing a model itself, but the whole pipeline, including data pre-processing, working on model architecture, training the model, hyperparameter search, and so on and so forth. Another cost is, of course, computational resources. We all can observe great projects from DeepMind or OpenAI, where they train their models using thousands of GPUs and spend enormous amounts of money for that. And of course, finally, we have some other costs. So for example, it can be, for example, management costs. And if you look at the plot, so here we have human level of performance. And of course, much below that, we can have, for example, performance of an average ML project. And when you are providing machine learning services to your customers, the problem is that very often this is what they expect, and this is how much they are likely to pay. Yes, and having all this in mind, there are two questions that I would like to at least try to answer during the rest of the talk. So the first question is how we can lower down the development cost to faster achieve human level performance. And the other is if achieving human level performance is intractable. So for example, because of not having enough resources, can we establish a smart cooperation between a human and a machine learning algorithm to keep both the level of accuracy and automation high? Okay, so now let's move to the second part of the talk, so to the human in the loop in the training phase. So in this part of the talk, I would like to show you one technique that can be particularly useful to reduce the cost of the project. And the technique is called active learning. So what is active learning? So it is basically just using human-in-the-loop approach to data labeling during the training phase. So look at the picture and imagine that you have a lot of unlabeled data. And this is very often the case in real-life scenarios. And active learning method selects a batch to label and presents it to the human. Human labels it, and the batch extends the training set, and the model is being retrained, and the loop closes. And what is important, active learning can drastically reduce the amount of data needed to train the model and significantly reduce the cost of the whole project. Usually you have to label only a small percentage of the whole data set to achieve comparable results as with the full data set. And this is because it labels the most informative data points instead of labeling the whole data set up front. Okay. And there is one particular method that I would like to show you. This is called BALT, which stands for Bayesian Active Learning. And I will focus on a version for deep learning models. So in general, an active learning algorithm decides what example to label next by maximizing something that is called an acquisition function A. And A takes an example X as the input and the current model. So, and different active learning algorithms have different acquisition functions, and BALT uses the mutual information between predictions and model posterior as the acquisition function. And in this equation, I stands for mutual information, H is the entropy of the distribution over Y, and E stands for expected value. And of course, you cannot compute this formula directly for deep learning models, but actually you can efficiently approximate it, for example, by using a technique called Monte Carlo dropout. And I will explain it in more detail in a couple of slides. And recently, a very nice extension of the BALT method came out, which is called the Batchboard method. And it works more efficiently with data batches. Okay, so here we have a comparison between BALT and Batchboard on MNIST. And these results are taken from the original paper of Batchboard. And on the y-axis, we have model accuracy. And on the x-axis, we have the number of data points that were labeled. So we can see that after labeling about 250 examples, the method is achieving the accuracy of over 95%. And you can also see that Batchboard is less sensitive to the batch size than the basic BALT method. Okay, so now let's move to the last part of the talk, so to the human in the loop in the predictions phase. Yes, and I would like to start with something that I call the accuracy automation trade-off. So the idea is that by incorporating a human into the prediction process, we would like to gain from automation as much as possible while keeping the accuracy high at the same time. So look at the picture. Having a new input example, we should first decide whether this example is easy enough to be processed by a machine learning model, or maybe it should be processed by a human, because there is a high risk that the model may make an error and the total accuracy may drop. So the method here, which we call the dispatcher, is basically forwarding the examples either to the model or to the human. And the level of automation is just the percentage of the examples that are forwarded to the model. So, in other words, the dispatcher is just an auxiliary algorithm that is to address the optimization problem, where we are trying to maximize the automation while keeping the accuracy above some threshold. And this threshold can be, for example, human level performance. And here is a very basic idea on how we can develop a baseline method for the dispatcher. So for each class C, we would like to set a threshold lambda C that if only the probability of class C for a given input X is above this threshold, then the chance that our model may make an error is less than some given threshold epsilon. So we can actually treat those lambdas C's as additional hyperparameters, and we can estimate them, treat them like classification threshold and estimate them just by using regular close validation. And the baseline method for the dispatcher is then as follows. So for the input X, if there exists a class that the probability of the class is above the class-specific threshold lambda C, then we go for automated track. And otherwise, we have to process the example manually. Okay, and the main problem with the baseline method is that deep learning models are usually bad at estimating uncertainty. What I mean by uncertainty here is just estimating the true probability distribution over Y. And this is where the Bayesian approach comes into play, because it aims to mitigate this problem by using something that is called the predictive posterior, rather than model itself to estimate the conditional probability. And if you are not familiar with the Bayesian methods, you can think of the predictive posterior as of the model that is the result of taking weighted mean of different set of the parameters of the model, and the weights in this weighted mean are computed accordingly to the predictive power of each set of the parameters. Yes, and one of the most common ways to approximate predictive posterior for deep neural networks is Monte Carlo dropout, which was also used to approximate the bold acquisition function that I was talking about a few slides ago. And without going into details, the idea is that you are randomly generating predictions by turning on and off different parameters omega using dropout, and then just take a mean of the generated predictions. Yes, and here are some results on MNIST. In this experiment, we trained a multi-layer perceptron on the examples from the classes 1, 2, 3, 5, 6, 7, 9. And for testing, we used the full test set, where images from the classes 0, 4, and 8 were used as out-of-domain examples. And what you can see in the plot is the visualization of the accuracy automation trade-off. So on the x-axis, you can see an expected level of accuracy. So this is our constraint. And on the y-axis, you can see the level of automation that we are achieving. Yes, and it is quite obvious that the higher the accuracy we expect, then the more examples will be forwarded to the human, so the level of automation will be lower. And note that the Bayesian method significantly outperforms the baseline approach, especially when the expected accuracy goes up, so in this area. And taking into account that the level of automation is actually equivalent to the money savings that we will have, I would say that this is the right moment to say that it pays to be Bayes. Okay, and finally, I would like to show you another approach that we are currently working on. And this approach, we use another model as the dispatcher, which is trained jointly with the predictive model using the loss function L that ties them together and is given as follows. So here we have the equations, how we can evaluate the loss function. And without going into details, look at these two animations. So on the left, you have a regular logistic regression model fitted to the data you can see in the picture. And you can see that it achieves 90% of accuracy. And on the right, you can see the situation when it is trained jointly with the dispatcher model. And the dispatcher is this yellow line here. And the dispatcher achieves 94% of automation, and it is dividing the input space into two parts. And the model on each part of the space is actually now achieving 98% of accuracy. And basically, this is the whole idea. And again, here you have results on NIST. So the experiment setup was exactly the same as before. We used logistic regression models with convolutional neural networks features. And we can see that the model, the two-model approach, which is here the last bar, the purple bar, slightly outperforms the baseline method, but for now it definitely requires more work to be done to be something useful. Okay, so to conclude, I would like to point out two things. So the first is that from business perspective, having accuracy at the level similar to human level performance is very often a must-have. And maximizing the level of automation is what brings the value to the business. And the second is that to address the business need, we have to either find a way to lower down the cost of development of highly accurate machine learning models, or develop the techniques for smart collaboration between humans and algorithms. Okay, and that's it. So thank you for listening, and now feel free to ask some questions. Thank you.
So yeah, hello, Adam, are you there?
Yes, I'm here. Hello.
Yeah, great. So let's start with this quick question, which I assume would be very quick to answer. Can you recommend some tools that make it easy to orchestrate active learning in commercial products?
So okay, so basically we are not working with any library because we are just using the BOT algorithm itself, but there are a couple of frameworks for Python. The one that I know is called modal, and basically it has a couple of algorithms implemented, so you can try this one if you want to start working with active learning.
Okay, So the second question, should we select points which the model is least certain with respect to classification prediction, or points that are good representatives of the underlying, I guess, distribution, to make information propagate?
So selecting the representative points for the distribution, I would say, is not enough. So the idea is just to identify the region in the feature space where the model achieves very high accuracy. So it is not making, it is almost not making any error. So yes. So, but sometimes even selecting the regions where model is certain would not be enough, because if the uncertainty is estimated wrongly, then model can be very certain of a prediction, but it can make an error anyway. So the idea is just to select the regions where the model is where the model is not making error, or is making very little of error.
Okay. So the last question from the audience, did you consider any other acquisition functions, and what are the trade-offs between them? How do you select the best?
In active learning case, we're using BALT because this is something that works for us, but the main criterion for selecting the acquisition function should be how fast the model is learning. So better the acquisition function is, then faster the model will learn to achieve very high accuracy.
Okay, so we don't have any more questions, but we have some time. Do you have any, maybe do you see any connection between automating humans and maybe incorporating humans and approach of GANs? I mean, like, I mean GANs with human, which is the generator kind of.
Yeah, absolutely. So I would say that GANs as unsupervised models is also a way how you can somehow do the density estimation over the input space. And of course, there must be a way how you can use GANs just to select which observation should go to be manually labeled and which one should be labeled automatically.